This conference will now be recorded.
Yeah, today we'll be discussing on HDL, that is hardware description language. Okay. So in the last class we have discussed about basics of HDL. Is that correct? Why we require HDL and all. Correct. So I'll just share one PPT here. Just check. Can you see this? Yeah. Can you see this?
Yes, sir.
Yeah.
Yes.
Yeah. So hardware description language, it has got two parts. One is VHDL and one more is Verilog HDL. VHDL means it's a very high speed integrated circuit hardware description language, and one more is Verilog HDL. So basically, what do you mean by HDL? It's a hardware description language that mainly describes the hardware of the digital system. So the main thing you require is, say you are writing one program in HDL. So what you need to have is, you should know the description of the hardware. Say you are designing one hardware, half adder circuit. So to write the code, you should be knowing the description of the adder circuit. Means how many inputs you require and how exactly output and all. Okay. So one can design any hardware at any level. Simulation of designs before fabrication. So basically we are using the HDL for designing of IC. Right? So before the fabrication we are using HDL. With the advent of VLSI, it is not possible to verify a complex design with millions of gates on a breadboard. HDLs came into existence to verify the functionality of this circuit. Okay, so if the say we have one IC with millions of gates, right? Then what happens is, if I want to check the connectivity within that IC, means it would be very difficult. So what we are doing is, we are analyzing such circuits or the system with the help of HDL. So HDL, it's a CAD tool that can be used to simulate or synthesize any digital system. Okay. So next one is, yeah, as I have explained, Verilog and VHDL. There are two parts. Verilog simulator, we have many types of simulators used in Verilog HDL. That is, first one is Xilinx, second one is Veriwell, third one is Model Sim. So in our lab, we are using Xilinx simulator, that is 9.2 version. So using this simulator, what we can do is, we can analyze or we can design any of the electronic circuit. So for that, say we have one AND gate. So we are writing a code for realizing or checking the functionality of AND gate with respect to, say, Verilog code. So for that, we need to write the code in Verilog. Okay. So after writing the code in Verilog, next we are checking the simulator part. Means we will check how exactly it works with respect to your simulator. Once it is working, means that same code we can dump onto the kit. So that converting that code into a schematic, that procedure is called as synthesis. Using RTL synthesizer, we are doing that. Okay, that we'll see later. So basically, the simulator we are using is Xilinx, that is 9.2 version. Then levels of abstraction. Mainly, there are 4 different levels of abstraction in Verilog. First one is behavioral, data flow, gate level, and switch level. Means these are the standards, or you can write any of the HDL code in these 4 formats or levels. So a Verilog program for a particular application consists of mainly 2 blocks. One is design block and one more is testing block. Design block, 2 types of design methodologies are available here. First one is top-down design, second one is bottom-up design. So for this design block, we need to give the input, and depending on the inputs, it will produce the output. Okay, first we'll check top-down design. So in top-down design methodology, we define the top level block and identify the sub-blocks necessary to build the top level block. We further divide the sub-block until we come to the leaf cells, which are the cells which cannot be divided. So we can see here. So this is the top level block, right? So we'll start from top level block, and we'll go on dividing this top level block till the leaf cells, which are the cells which cannot be divided further. Okay. Second one is bottom-up design. So in a bottom-up design methodology, we first identify the building blocks. We build the bigger blocks using these building blocks. So these cells are then used for high level block until we build the top level block in the design. So clear? So in the first one, top down design. So we'll start with top level and we'll go on dividing. Okay. So in the second one, it's a bottom up design where the process is exactly the reverse one. So example for example, we can take 4-bit adder, 4-bit ripple adder or ripple carry adder. So first thing is it's a 4-bit ripple carry adder. Then we require 4 full adders here. Okay, 1, 2, 3, 4. So this full adder again we require how many gates here? XOR gate, AND gate, OR gate. So these third one, these we can call it as leaf cells. We cannot further divide this further. So for each full adder, we require 1, 2, 3 gates. For second full adder, again 3 gates. Third one, 3 gates. Then fourth one, 3 gates. So I can call it as a top-down approach. Okay, or top-down design. Okay, so next is module representation. And one more thing I would like to clear is, as I told you, we have got 2 types. One is VHDL and one more is Verilog HDL. In case of VHDL, we have got, means say we are writing any code in VHDL, means we need to write in such a way that it should have two main parts. First part is entity part, second part is architecture part. In case of VHDL, so entity, what it does, it will show all the inputs and outputs, whether it can take single bit, 2 bits and all. Okay, and architecture is that part of the program which basically show the relationship between inputs and outputs. So that architecture again we are connecting to the entity part. Okay, this we are doing in case of VHDL program or VHDL code. Okay, but in case of Verilog code, instead of having entity and architecture, we have got a single part, that is module. Within the module, we are assigning all the inputs and output ports, and we are showing the connectivity between inputs and outputs. So in your subject, we are dealing only with the Verilog HDL. Okay, so we are using module. So a module is a basic building block in Verilog. It can be a single element or collection of lower design blocks. A Verilog code starts with module. Okay, a Verilog code starts with module, then module followed by inputs and outputs. Okay, then once we assign all the inputs and outputs, so the next thing is we need to show the connectivity between your inputs and outputs. So next one is input output definition. Once the module is defined, at the start of the inputs and outputs are to be defined explicitly. For example, input A comma B means there are two inputs, that is A and B, of 1 bit each. Means A can take 1 bit at a time, either 0 or 1. Similarly, B can also take only 1 bit at a time, either 0 or 1. If input or output is more than 1 bit, that is 2 or 3 bits, then the definition will be like this: input 3 is to 0, A comma B. Mean to say is 0 is the lower limit and 3 is the maximum limit. Means A can take 4 bits at a time. A can take 4 bits at a time. Means 0000 to 1111. Similarly, B can also take 4 bits at a time, like 0000 to 1111. If that is the case, then we need to show the like this: 3 to 0. Similarly, output is C, a single bit which will also hold 4 bits at a time, like 0000 to 1111. Next, levels of abstraction. So gate level modeling. So in gate level modeling, a circuit can be defined by use of logic gates. So these gates are predefined in Verilog library. The basic gates and their syntax is as follows. So AND gate, OR gate, again can take two inputs and will produce a single output. XOR gate inputs the single output. Then NAND gate, NOR gate. And remember, NOT gate is the only gate which will take a single input, right, and produce a single output. So this is the data flow modeling. Continuous assignment statement is used. Keyword assign is used followed by equal to sign. Most common operator types are operator types, operator level, operation performed, and number of operands. So first, the operator we are covering is arithmetic operator. So in this arithmetic operator, I can show multiplication, division, addition, and subtraction. So operation is multiply, divide, add, subtract. And you need to remember one more thing is in Verilog HDL, mainly we are using symbols instead of words or notations. Then number of operands means if you are performing multiplication operation means you need to have two operands. Similarly, for division, two operands; for addition, two; and for subtraction also we require two operands. Then bitwise logical means bitwise negation. Negation means I can say it's a NOT gate. Then bitwise AND, then OR, XOR, XNOR. Again, for all these operations, we require two operands. Then shift operations, shift left, shift right, concatenation. Okay. Then last one is conditional. These we'll see later. So we'll check some examples here. Assign x equal to a plus b means you are adding a with b. Means a and b will be your inputs and x will be the a and b are inputs and x will be your output. Okay, and the output will be stored at x. Assign y equal to negation of x means x is input, y is output. So whatever the input you are giving to x, that will be complemented by your output. Say you are giving x as 0 means you'll be getting at the y as 1. Next one, assign y equal to a and b means you are doing the AND operation. Then this is XOR operation. Assign x is greater than 1 means you are shift writing x by 1 position. Okay. Then assign y equal to b comma c. Like for example, b equal to 3 dash b 1 0 1, c equal to 3 dash b triple 1. After concatenation, I am getting output as 1 0 1 1 1 1. Next, module instantiation. It's a process of connecting one module to another. For example, in a test bench or stimulus, the top level design has to be instantiated. What do you mean by test bench is, say you are writing one code or Verilog code, right, to realize one AND gate. Okay, so first what we are doing, we are taking one module, that is Verilog module, then we are assigning inputs and output, then assign y equal to a and b. So that is the connectivity between inputs and outputs. So for next is we need to check the whatever the code we have written, that we need to check for errors and all. So once it is working fine, next thing is we need to check the this one, check with respect to simulator. Simulator means AND gate, y equal to a and b means we require two inputs and one output, right? So how we are checking with respect to simulator? A and b are inputs, so I can give in 4 ways. Inputs can be given in 4 ways, like 0 0 0 1 1 0 1. Okay, when we can expect the AND gate output as high, if both the inputs are high, then we can get the high output. Getting right? Hello? Anyone?
Yes, sir.
Getting right?
Yes, sir.
Yeah, fine. So we are checking the AND gate, right? So for AND gate, y equal to a dot b, correct? So inputs are a and b. So if you write the truth table for AND gate, I can write like ab, then y equal to a dot b. Okay, you can assume that ab 0 0 0 1 1 0 1 1. Then output y equal to a dot b means output will be high if and only if both the inputs are high. So I'm getting output as high only for the last iteration, correct, right? So for that we are using test bench and all, that we'll see later how exactly it works and all. We take Xilinx again, then I'll show you how to run the code and all with respect to simulator, that we'll see later. Is that fine? Is that fine?
Yes, sir.
Yeah, fine. Okay. Next would be testing blocks. Yeah. You can see two input AND gate here. So in this case, the inputs are A and B. Output is Y equal to A dot B. Right. The design and stimulus blocks will be as follows. So AND gate, same code I'm showing over here. So module name practice. See, it is not like you need to give the same module name like practice. You can give your own name. Module practice y comma a comma b means we are defining the module by the name practice. Okay, this is the definition. Then again I am showing the inputs here. A and b are inputs and y is the output. Right. Same thing. Then I'm using one keyword called assign. So this keyword we are using only in case of Verilog HDL. Right. After assign, I'm just showing y equal to a and b. Then end module. We started the module here by the name practice. I'm declaring all the inputs and outputs. A and b are inputs. Y is the output. Input a comma b, output y. Then assign y equal to a and b. So remember, I'm using only symbols in case of Verilog. Suppose say I'm writing the same, I'm writing the code in HDL. Then instead of module, I need to show two parts, entity and architecture. Inside entity, I am showing all the inputs and outputs. Then within the architecture, I'm showing this part, that is y equal to a and b. There, I'm not using assign keyword. So this assign keyword is only used in Verilog HDL. This we'll see later. Same 4-bit ripple carry adder, or even I can say it's a parallel adder. Right. So 4-bit parallel adder. So this is one full adder. Bottom level module. So in bottom level module, we will start with the leaf cells. Okay. So module full adder, sum, cout, AB, IO port declaration. Then outputs are sum and cout. Inputs are AB, CIN. Then internal nets. So this part we will check later. Wire S1, C1, C2 and all. Okay. Top level module. Again, it is for 4-bit adder. Module top level sum, cout, ABC, AB and CIN. IO port declaration. Same. Output sum. What is the limit here? Outputs are two here, sum and cout. Whereas sum, it will can hold 4 bits at a time. Therefore, we are showing it as 0 to 3 to 0. 0 is the lower limit and 3 is the upper limit. And output is cout, means it can hold a single bit. Okay, because that is the carry part. Right? Again, inputs A will take 4 bits at a time, say 0 0 0 0 to 1 1 1 1. Similarly, B can take 4 bits at a time, 0 0 0 0 to 1 1 1. Okay. Input is same. So scene can hold a single bit at a time, means it can take either 0 or 1. Then internal nets wire C1, C2, C3. Okay, this part we'll check later. Okay. I think in the third module we'll be discussing on this. So clear? When we need to show the range, if the inputs are outputs are taking more than 1 bit, then we are supposed to show the limits. Right? So next is test bench. Test bench means, so this can be used in simulator part. Verilog keywords. Verilog uses about 100 predefined keywords. All the keywords are presented in colored font, either green, blue or red. If it is not shown in a colored font, it means there must be some typing error. So you need to remember that whatever the predefined words we are showing in Verilog, okay, they are in colored font. Okay. Then all the Verilog statements are terminated with a semicolon. See, the syntax of HDL code or your HDL is same as that of C language. Correct, right? So in C, what happens is for ending the statement or end of the statement, we are using semicolon. Same goes with your HDL code, right? So syntax is almost same as your C language. Okay, but remember one thing. Whatever the code you are writing, that code basically defines the hardware of any electronic circuit. Fine. All the Verilog statements are terminated with a semicolon, except for the statements keywords like initial, begin, and always. So these statements will not have semicolon. Other than these keywords, right? Now, if you are ending the statement, means you're at the last it should have a semicolon. Verilog is case sensitive. Remember this. VHDL is case insensitive, whereas Verilog is case sensitive. That is, the keywords are written in the lowercase. Okay. Most common keywords are module. At the beginning of the code, we are showing this module. At the end of the code, we are showing end module, input, output, wire, register, display, print, monitor, always, initial, begin, and or not. These are the most commonly used keywords in Verilog HDL. Then single line comment is given by two consecutive slashes, and multi-line comment is given by this way. Okay. So any doubts here? Any doubts? Any doubts? Following right? Abhinandan? Abhinandan?
Yes, sir.
Yeah. Till now, if you
Yes,
have
sir.
any
Yes, sir.
doubt, if you have any doubts, you can ask me.
So, no doubt, sir.
Clear, right?
Yes, sir.
So remember one thing, and why we are using HDL? Say you are designing any of the digital system. Getting my point?
Yes, sir. Yes, sir.
You are designing it, the IC, directive design. First thing is, right? First thing is you need to understand the hardware, what it is and all, right? Then according to the hardware, you are writing the code, right? Once the hardware is ready, once the code is ready, you are checking the code with respect to simulator. Getting with respect to simulator means we are checking the code with the help of test bench waveform. As I explained, two input AND gate. So AB are inputs, C is the output, right? If the inputs are 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, and 1, 1, your output will be high if both the inputs are high. That we are checking with respect to test bench waveform. That is called as simulator. So once it is working fine means we can convert that HDL code into a schematic or a circuit. So that once it has been converted means that that RTL schematic that is being dumped uh, onto the FPGA kit. FPGA means it's a field programmable gate array, right? So it's a Spartan kit. So on that you can find n number of gates. Okay. So in say you written one code for or to analyze or realize one AND gate, right? So once you are dumping that code onto the kit means out of n number of gates, only two input AND gate will be enabled. Okay, so once it is fine means then we can go for fabrication and all. That is the final stage of your IC. Hope you are getting me.
Yes, sir.
Clear? So next
Yes, sir.
is fabrication and all. Okay, that part is covered in VLSI. Fine. So shall I continue? Any doubts here?
Yes, sir. Yes, sir.
Any doubt? Okay. So HDL is a language from class of computer languages, right? It is a textual description consisting of expressions, statements, and control structures. It allows for the automated analysis, simulation, and simulated testing of any electronic circuit. Fine. Okay. Now we'll see. What do you mean by simulation? First, it is used to write a model for the expected behavior of the circuit before that circuit is designed and built. The model is fed into the computer program called a simulator, which allows the designer to verify that the solution behaves correctly. This process is known as hardware simulation. So once it is working fine, so next part would be synthesis part. So it is used to write a detailed description of a circuit that is input into another computer program called a logic compiler. The output of the compiler is used to configure a programmable logic device such as FPGA to perform the hardware function. This process is called as hardware synthesis. Right. So that code is dumped onto the FPGA kit. Then again, we can check. It is same like your. It looks like your LD kit. Okay. There we are checking checking the working of your gate with respect to the truth table. Like A, B are inputs and C is the output means with respect to your AND gate. If you are giving both the inputs A and B as high means the LED should glow in the kit. If that is the case, then you can conclude that your AND gate, whatever the code you have written, that is been working fine. Right? So what are the uses of HDL? To write the executable specifications for hardware, to model a piece of hardware before it is created physically. Okay. So before the actual design, we are using this HDL. It is executably that gives HDLs the illusion of being programming languages. They are more precisely classified as specification languages or modeling languages. Simulators capable of supporting discrete event or digital and continuous means analog modeling exist, and HDLs targeted for each are available. So different levels of abstraction. First one is architecture or algorithm level. Describe the functionality or behavior of a circuit. Second one is RTL, that is register transfer level. Describe the data flow of a circuit. Gate level. Describe the connectivity, that is structure of a circuit. And last one is switch level. Then design flow of using HDL. So first we should have idea what exactly you're designing and all. Then Verilog behavioral model. This is just a flowchart. Verilog Excel verification, synopsis, logic synthesis, Verilog structural model, then Verilog Excel verification, and all. This we'll see later in detail. Why use the HDL? It is difficult to design directly on hardware. Okay, so what we are doing is before we are checking the code with respect to our Xilinx, that is the simulator. The next level is we are checking onto the kit. Mixed level modeling and simulation, easier to explore different design options, reduce design time and cost. Okay. So types of HDL, as I told you, mainly there are three types. One is VHDL, Verilog, and one more important one is system Verilog. So VHDL and Verilog are considered general purpose design languages, while system Verilog represents an enhanced version of Verilog. Each has its own style and characteristics. VHDL has roots in HEDA programming language in both concept and syntax, while Verilog's roots can be tracked back to an early HDL called Hello and the C programming language. System Verilog includes a set of extensions to the Verilog HDL to help the engineers design and verify larger and more complex designs. Okay. Verilog is similar to C. VHDL is similar to ADA. Popular in commercial. Okay. Popular in military applications and all. And one more thing is in Verilog, design mainly contains the model part. In case of VHDL, it contains two parts, entity and architecture. Advantages of HDL. Advantages compared to traditional schematic based design. Design with RTL description, logic synthesis tool, abstract level. Second one is independent to fabrication technology. Reuse when fabrication technology is changing. Functional verification can be done early, that is optimized to meet the desired functionality. Analogous to computer programming, textual description with comments. So software conclusion, software programming languages and HDL are very different languages because both have many basic level differences, even if they seem to have a few similarities. In contrast to most of the software programming languages like C, HDL includes an explicit notion of time, which is primary attribute of hardware. Okay. So any doubts? Any doubts?
No, sir.
Okay, clear it. Initially, it looks a bit difficult. So once we start writing the programs using Verilog, then it will be easier. So next class onwards, what we'll do is I'll show you how to write the code with respect to your hardware. Is that fine? Is that fine?
Yes, sir.
Yes, sir.
You can take 2 minutes. If you have any doubts, then please let me know. Sudha, any doubts?
No, sir.
Ajay Kumar?
No doubts, sir. No doubts.
No doubts. Okay, fine. So clear at main concept. So
Yes, sir. Clear.
before designing any of the digital system, the initial level is we'll start writing the code. So how we are writing the code with respect to the hardware. So how exactly your hardware works. So as I've told, say you have one half adder. So half adder, what it does, it adds two inputs and generates two outputs. Correct, right? So the code, whatever you are writing, right? So it should reflect your hardware description. Getting. So first we will start with module name, then followed by inputs, two inputs and two outputs. Then we need to show the connectivity between inputs and outputs. So assign output, say sum equal to a XOR b, then assign carry equal to what it is, a and b. Then we are ending the module. So that is the flow of your Verilog code. Suppose if you are writing in VHDL means we are showing the code in two parts. First one is entity part, where we are showing only all inputs and outputs. Then in the next part, that is architecture, we are showing the relationship between your inputs and outputs. But remember, we are not using any keyword called assign in VHDL. That is being used only in case of your Verilog HDL. Okay. So any doubts? Any other doubts? And main advantage is you have both the simulator and synthesizer. Using simulator, you can check whatever the code you have written, is it working or not. So using test bench waveforms. So once it is been done, then you can dump the code onto the kit. So before that, we are converting that code into schematic or circuit. That process of converting your HDL code into a schematic is called as synthesis. That will be checking in lab and all. Then it could be easier for you. Is that fine? So any other things from your end? Anything else?
No, sir.
Is it fine?
Yes, sir.
Yeah.
Yes, sir.
Next class we'll be discussing on different types of methods. Like we have mainly data flow model methods in the sense models. How many ways you can write a Verilog code? So first one would be data flow model. Second one is behavioral model. Third one will be your structural model. So next class we'll be covering all these different ways. Okay. Any doubts? Any doubts?
No, sir.
All right. Yeah. Thank you. Thanks for joining.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.